Hello, Algebra 1 students. Trying to get my music to start here. We're going to listen to Adele while we work today. I know I have some Adele fans out there somewhere. But we're talking about radical expressions, simplifying radical expressions today. There's Adele. And I thought this one was kind of funny. Please don't try this on your quizzes with me. Write a single radical expression. That's totally gnarly, dude. Well, we're going to be looking at simplifying radical expressions that involve multiplying in this video, and only multiplying. So let's get started with a little bit of a review of the real number system. All right. Now recall, okay, that you've got real numbers. Real numbers are the numbers that can be used in real situations in the world. And there are two basic categories. You got your rationals and your irrationals. Rational numbers, remember, can be expressed as fractions. Yes, that includes repeating decimals, because 0.3 repeating is 1/3. And it includes radicals where the radicand, the number on the inside, is a perfect square. And I love how they use this example. The square root of 0.25 is 0.5. And that's also expressible as a fraction, 1/2. Once you start winding down the rational numbers to the integers, now that's where we have, you can express it as a positive or negative whole number. So -3, this has a value of -2 right here. The square root of negative square root of 16 is -4. Okay, so your negatives don't necessarily need to be integers. Notice back here, -2/3 is not an integer because you cannot express it without a decimal or a fraction. You have to express -2/3 as a fraction or a repeating decimal. If it were a repeating decimal, it would be -0.6 repeating. And we should know our basic repeating decimals. All right, then you get more specific. You take out the negatives altogether and you get the whole numbers. And the number 0 is the only number that is a whole number and an integer, but not a natural number. Okay, so 0 has a whole in it. It's a whole number. Other whole numbers would be what's in this natural number category. This is equal to 2 right here. This is equal to 5, and then the 7 there. So whole numbers that don't have negatives and aren't 0 are natural numbers, the counting numbers. If you take out all of those values that can be expressed in an exact manner without a calculator, you have over here the irrational numbers. Irrational numbers do not terminate, do not repeat. You get instead a value. For example, pi is between 3 and 4. It is approximately 3.14, but we know that you can keep those digits going. I've just asked a few of your classmates who memorized quite a few of them back in March. Okay, what about the square root of 10? Now, the square root of 10, not a whole number, can't be expressed as a fraction. Cannot be expressed as a fraction because rational numbers over here, rational, can be expressed as a fraction, irrational. The whole definition is no fractions. Cannot be expressed as fractions. So I know some of you tried when you had a radical, when you were dealing with the quadratic formula, you tried to find the fraction value for a square root, and it didn't work, and you were like, it's not working. Well, right, because you can't. You can't express that number as a fraction. But I can go ahead and take the square root of 10, and I can approximate it. Why can't I find my radical sign in my calculator? Oh, there it is. Square root of 10. Square root of 10 is approximately 3.16. Okay, so I can approximate it, but I can't say an exact value. And that's the real number system. Okay, let's keep going. Now, why did I do that? Well, because a radical expression contains that square root sign. Okay, contains a square root sign. So the square root with a number inside. Okay, or a value. And we're going to start off with numbers, and later we'll have algebraic expressions in there. A radicand, the radicand is the number inside that radical sign that would be in here. All right, some examples. Let's look at some examples. All right, square root of 25. Right, square root of 33. Square root of 24x cubed. These are all examples of radical expressions. Now, whether or not it's simplified, totally different issue. There's 3 steps or 3 rules to simplifying radicals. First of all, the radicand has to have no perfect square factors other than 1. So square root of 25 is not simplified. Square root of 33 is, because nothing that's a factor of 33 is a perfect square. The radicand contains no fractions, so you can't have a fraction underneath the radical sign either. And finally, no radicals appear in the denominator of a fraction. Now we're going to be dealing with the second and the third stipulation on this list. We're going to deal with those in the next video. Today we're just going to stick to the radical having no perfect square factors other than 1. Let's talk about the difference between exact and approximate. Alright, an irrational number is a decimal value that does not terminate and does not repeat. We established that on the first slide in this video. Okay, the whole definition of irrational numbers, not expressed as a fraction. So it doesn't terminate, doesn't repeat. A simplified radical expression where the radicand is a number is an exact value for an irrational number. So when I say square root of 33, that is exact. And that's how we leave it. You wouldn't write the decimal down because that's no longer exact. And this is very similar to what you may have learned last year with regard to circumference and diameter, or circumference and area of a circle. That you can give the exact circumference or area by keeping the radical sign in the answer, the pi symbol in the answer. Or you can approximate it by punching it in the calculator and rounding it off. And that is what happens here. The value given by a calculator for a square root of a non-perfect square is an approximation only because it must be rounded off to a specific decimal place to be expressed as a decimal. So square root of 33, grabbing my trusty calculator. My trusty calculator is also the source of my music because it's my iPhone. So I apologize if the sound changes. Square root of 33 is approximately 5.74456264 blah 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 blah. So 5.7. It's no longer exact. I can say, well, it's about 5.7, but that's not exact anymore. So exact versus approximate. Keep the radical sign for exact. Punch it in the calculator for approximate. Okay, let's look at this rule. This is the only rule we're covering tonight. 3 pages of examples and we're done. When a is greater than or equal to 0 and b is greater than or equal to 0, the square root of a product, ab, can be split apart and become the square root of a times the square root of b. Doesn't work with addition or subtraction. Division we'll come to in the next video. Only with multiplication. The square root of 48 is equal to the square root of 16 times the square root of 3. And a simplified version of the square root of 48 is 4 root 3. And that's how we say that, or not pronounce it so much as read it. This is read 4 root 3. Okay, 4 times the square root of 3, 4 root 3. And that's the exact value for the square root of 48. So let's try these two. So the first thing you're going to do is you're going to think of a perfect square that's a factor of 160. I thought of 16, just like the one we did in the example up top. Square root of 16 I can take, square root of 10 I cannot. And that's the rule you want to live by here. Split it up into the largest perfect square times the rest that you can think of, and then you're going to want to double check and make sure you got it right, and don't have any extra perfect square factors in there. Square root of 16 I can take 4 times root 10. Now stop and think. Does 10 have a perfect square factor? Oop, I didn't mean to erase that. I hit the wrong tool. Square root of 10. Wrong tool. There we go. Square root of does 10 have a perfect square factor? No. 10 only has 2 times 5. Those are the prime factors of 10. Neither one's a perfect square. So 4 root 10 is your simplified version of 160. How about 72? Now, you may not recognize it, but 72 is a perfect square times 2. And if you didn't recognize it, hopefully you'd be able to figure it out as you went along. Like, say that you found it was square root of 9. Okay, we'll do that in a second. So let's finish this first. Square root of 36 times the square root of 2 is 6 root 2. Say that you didn't see the 36. Say that you thought, 9. 9 is a perfect square. All right. Square root of 9 times square root of 8. Well, square root of 9 is 3 root 8. But 8 still has a perfect square factor. 4 times 2. So you could do another step. So even if you didn't recognize that you could simplify it further, or that you could have picked a larger perfect square, you can simplify it further later. So 3 times 2 times the square root of 2, or again, 6 root 2. So what happens when you have variables involved? Well, you're going to find the square root. Okay, well, notice again, we're talking about values that are positive only, so we're not worrying about the possibility of negatives here, not on the inside of the radical sign at least. You can do the same thing you did before. You're going to find perfect squares and leftovers. So 9 is a perfect square times 6 for 54, and 6 doesn't have any perfect square factors. But you're going to do the same thing with the variable. You're going to make it x to the 6th, because 6 is even, times x. Because I can take the square root of an expression that has an even exponent, but I can't take the square root of just an x or an x that has an odd exponent. So now I'm going to go through and take the square root of whatever I can take. Okay, I can take the square root of 9, and I can take the square root of x to the 6th. And that's going to be 3 and x to the 3rd. I cannot take the square root of 6, nor can I take the square root of x. And this is the end of the problem. This is the simplified form of this. Okay, let's try the next one. A negative m on the outside has no impact on the answer here. Perfect square that's a factor of 80. Well, 16 is a factor of 80. 16 times 5, in fact. So it wouldn't hurt in the classroom to, it definitely helps if we know our times tables really well, but some of these values are going to be a little big. It never hurts to use a little bit of calculator trial and error and say, does 16 go into 80? And then check. Okay, look for those bigger perfect squares. And then as you see, I split m to the 9th up into m to the 8th times m. Okay, I can take the square root of this and this. So that's 4. So I have negative m times 4 times m to the 4th with the square root of 5m left inside. And now I'm just going to go ahead and multiply this and simplify it a little. So the negative is going to go on to the 4. You got an m to the 4th on the outside and a 5m on the inside. And that one's also done. Last slide. So just as, I think I made a mistake on this bottom one. I did definitely make a mistake on the bottom one. Hold on. All right. I apologize for the editing jump and for starting the song over again, but I realized very quickly that there was something wrong with what I was doing here because this bottom expression was wrong. So I have now fixed it, moving forward. Okay, so if I can take apart a radical expression, so if I've got the product of AB and I can take it apart and make it the square root of A times the square root of B, I can put them back together too. And that's how we're going to deal with an expression like this one. So 2 root 7t times 3 root 14t squared. And we're going to start off by using our commutative property and rearranging. And then we're going to take everything inside that radical sign and put it together. So we've got 7t times 14t squared. Now I'm going to rearrange that as well. But I'm going to look for a way to make this a little easier for me to simplify. Instead of multiplying 7 times 14 and making the values bigger, I'm going to break it down and use prime factorization a little bit. I have the 7 from the beginning, and 14 is 7 times 2. The 7 from the beginning, and 14 is 7 times 2. Then I have t and t squared. And again, I'm not going to multiply it together unless I feel like I need to. And in this case, I don't, because t squared is a perfect square, but t isn't. So I can leave it separate. Now, if I was to multiply 7 times 7, I would get 49. But instead of multiplying that, I'm just going to think, all right, 7 times 7 is like a double factor. So that's a perfect square. A double factor is the same thing as a perfect square. So I have my 2 times 3 out front. And then I can take the square root of 7 times 7. And I can also take the square root of t squared. So that's going to be times 7 times t. And what's left inside is a 2t. Then all I have to do is multiply the outsides. 42t times the square root of 2t. How about the next one? Do the same thing. Nothing on the outside, so let's put it all together. And instead of 2 times 18, well, actually, in this case, 2 times 18, it actually makes sense, doesn't it? 36, 2 times 18. All right, so let's make sure we understand where that came from. I'm putting together the stuff inside the radical signs. So there you have it. There's all of it together, rearranged, because that's what the commutative property lets me do. 2 times 18, well, I do want to multiply that because that gives me a perfect square. Yay, perfect square. And a times a cubed gives me a perfect square too, a to the 4th. I can do this now. I can take the square root of 36 and the square root of a to the 4th. And there's no more radical sign in my answer. And remember what we said, the square root of a variable with an even exponent is going to be cutting that exponent in half. Let's just think about that real quick. Okay, square root of x to the 8th. Well, what times itself will give you x to the 8th? X to the 4th times x to the 4th. And so that's why we can take that exponent, cut it in half, and that gives us the simplified form of that, x to the 4th. And that's it for this video. All right, folks, radicals are pretty radical, dude. So I will see you guys in class. Yeah, that's it. I will see you in class.